Why is Earth so unique? Liquid water, presence of an atmosphere, more or less stable climate, very small temperature variations from 60 degrees to plus 50 degrees, presence of a magnetic field. Is all this accidental or was it created intentionally and for what purpose? Ever since we first looked up to the stars, humanity has been plagued by the same question: are we alone in the universe? Astronomers like Carl Sagan and Frank Drake have promoted an idea known as the mediocrity principle. It's simple: our Earth is an ordinary rocky planet orbiting an ordinary star in an unremarkable corner of one of hundreds of billions of galaxies. According to this logic, with so many planets, the universe should be teeming with life, including intelligent life. This optimistic view has fueled science fiction and the public imagination for decades. But what if we're wrong? What if our home isn't the rule, but an incomprehensible, almost impossible exception? In 2000, paleontologist Peter Ward and astronomer Donald Brownlee challenged conventional wisdom with their book and the unique Earth hypothesis. They argue that complex multicellular life requires such a rare combination of astrophysical and geological circumstances that our planet may be the only oasis of intelligence in the entire Milky Way and perhaps in the entire visible universe. It's an idea that has a chilling cosmic loneliness about it, but it also puts into perspective the wonder of our existence. Location matters, the galactic habitable zone. We talk about the Goldilocks zone, the ideal distance from a star where a planet can support liquid water. But Ward and Brownlee argue that there is another, much larger habitable zone, the galactic zone. Most of any galaxy, including our own Milky Way, is a dead zone, incapable of supporting complex life. The dangers of the center and the emptiness of the outskirts. Imagine the center of a galaxy. It's a seething cauldron where the stars are packed tightly together. Its chaos, gravitational disturbances from passing stars can easily throw planets out of their orbits, condemning them to eternal cold or falling into their star. But the main threat is radiation. The center of the galaxy is home to a huge number of neutron stars, black holes, and a supermassive black hole at the very heart. All of them emit powerful streams of X-rays and gamma radiation capable of sterilizing any nearby planets. Supernova explosions, colossal explosions of dying stars, occur much more often here, and their deadly radiation can destroy life at a distance of many light years. Okay, you say then you need to stay away from the center. But the outskirts of the galaxy are not the best place to live either. The problem here is metallicity, the content of elements heavier than hydrogen and helium. In astronomy, everything that is not hydrogen or helium is conventionally called metals. These elements are created in the depths of stars and are scattered across space after their explosions. It is from these metals that rocky planets like Earth are formed. There are few stars on the outskirts of the galaxy. They are older, and the metallicity there is too low. There is simply nothing to build planets suitable for life from. Thus, there is a narrow ring of life, the galactic habitable zone, where there are enough metals to form planets, but at the same time, it is quite safe from the deadly radiation and gravitational chaos of the center. According to various estimates, no more than 5 to 10% of the stars in the Milky Way fall into this zone. But even this is not enough. The development of complex life requires billions of years of stability. Therefore, the star must move in an almost perfectly circular orbit around the center of the galaxy so as not to cross dangerous spiral arms where the density of stars and the frequency of supernova explosions increase sharply. Our solar system is incredibly lucky. It is located right in this galactic habitable zone, and its orbit is almost perfectly circular and synchronized with the rotation speed of the spiral arms, which allows it to avoid frequent traffic jams on space highways. An ideal star and a unique system. Being in the right place in the galaxy is only the first point in a long list of requirements. You also need the right star and the right planetary system. The Sun is an atypical star. It is often said that our Sun is an ordinary star. This is not entirely true. Firstly, more than 50% of all star systems in our galaxy are binary or triple. In such systems, stable planetary orbits in the habitable zone are a rarity. The climate on a hypothetical planet would be completely unpredictable. Our Sun is a loner, and that's a big plus. Secondly, the Sun is a G-type star, a yellow dwarf, which is in perfect balance. Stars more massive than the Sun are much brighter and hotter, but they burn through their fuel in a matter of millions of years, not enough time for evolution. Less massive stars, red dwarfs, live for trillions of years, but they have their own problems. They are very dim, so the planet must be very close to them. This has two fatal consequences: tidal locking. The planet will always have the same side facing the star, like the Moon to Earth. One side will have eternal day and scorching heat, the other will have eternal night and freezing cold. Stellar flares, red dwarfs, are notoriously unstable and produce powerful flares that can blow away the atmosphere of a nearby planet. Our Sun is massive enough to provide a wide habitable zone, but stable enough to shine almost uninterruptedly for billions of years. Its luminosity varies by only 0.1%, an architecture built for life. The configuration of our solar system is also highly unusual. Most known planetary systems have super-Earths around their stars, planets several times more massive than ours. Inside, close to the Sun, are four small rocky planets, and beyond them are the gas giants in stable, nearly circular orbits. And this arrangement is our saving shield. Jupiter, which weighs 5 times more than all the other planets combined, acts as a cosmic bouncer. With its powerful gravity, it protects the inner solar system from the bombardment of comets and asteroids from the outer regions, such as the Oort cloud. It either absorbs them or throws them out of the system. A collision with Earth of the object that Jupiter took on in 1994, comet Shoemaker-Levy 9, would be guaranteed to sterilize our planet. Without the gas giants on the outer edges, Earth would be subject to catastrophic impact events much more often, making the evolution of complex life impossible. Earth and its faithful companion, a cosmic incident. Even with the perfect star and system, the planet itself must have a number of unique characteristics. A planet of the right size, the Earth is the right size. If it were smaller, its gravity would not be able to hold onto a dense atmosphere and it would become like Mars. If it were much larger, it would hold onto an overly dense initial atmosphere of hydrogen and helium, turning into a gas giant or mini Neptune. The birth of the Moon, the catastrophe that gave birth to life. But the most unique feature of the Earth is our Moon. It is abnormally large relative to its planet, the largest satellite in the solar system relative to the size of its host planet. According to the most convincing theory, the Moon was formed as a result of the collision of the proto-Earth with a Mars-sized planet called Theia about 4.5 billion years ago. This catastrophe had several consequences that were critical to life. Axis stabilization. The Moon's gravity stabilizes the tilt of the Earth's axis of rotation, currently about 23.5 degrees. Without the Moon, the tilt would fluctuate wildly, leading to extreme and unpredictable climate changes. A stable tilt ensures predictable seasons, an important stimulus for evolution. Tides, powerful tides caused by the Moon's proximity early in Earth's history, may have created ideal primordial soups in coastal areas where organic molecules would have concentrated. Tides may have later helped life to emerge from the ocean onto land. Plate tectonics and magnetic field. The giant impact may have given the Earth extra angular momentum, increasing its rotation speed and contributing to the formation of a large iron core. The rapid rotation and liquid core create a powerful magnetic field that protects the atmosphere and life on the surface from harmful solar winds and cosmic radiation. Plate tectonics may also owe their existence to this event. It plays a key role in the carbon cycle, regulating the planet's climate on geological timescales, the greatest filters from cell to mind. Even if all the astronomical and geological conditions were right, we are faced with biological barriers that may be insurmountable. The accidental origin of life, abiogenesis. The first step is the emergence of a simple molecule capable of self-copying replicator from non-living matter. This event must have happened by chance. The probability of this happening is so small that it is difficult to comprehend. Evolutionary biologist Evgeny Kunin estimates the probability of the spontaneous emergence of the simplest replicator as 1 chance in 10, 10, or 18. This number is so high that even over the entire existence of the universe, such an event might not have happened. Perhaps we were just incredibly lucky. Leap to complexity, eukaryogenesis. The first forms of life, bacteria and archaea, were extremely primitive. Their development stopped for almost 2 billion years. Evolution reached a dead end. For the emergence of complex multicellular organisms, a revolutionary leap was necessary: the emergence of a eukaryotic cell, a cell with a complex internal structure and nucleus. The leading theory is that this happened through a unique symbiosis. One cell, an archaea, engulfed another, a bacterium, without digesting it. This bacterium turned into a mitochondria, the cell's powerhouse, which gave it a huge amount of energy for further complexity. Biochemist Nick Lane argues that this event could only have happened once in the entire history of life on Earth. The emergence of intelligence, even in the presence of complex life, the emergence of intelligence is not a guarantee. During the 500 million years of the existence of multicellular organisms on Earth, up to 500 million species have emerged, according to various estimates, and only one of them developed technological intelligence. Evolution does not strive for intelligence, it strives for adaptation. A long trunk in an elephant or the ability to echolocate in a dolphin are as extreme as a large brain in humans. Dolphins had 20 million years of evolutionary advantage, but they didn't build a radio telescope. The emergence of intelligence is perhaps the rarest of all accidents. Criticism and alternatives, anthropocentrism or reality. Of course, the hypothesis of a unique Earth is not without its shortcomings and is subject to criticism. The main reproach is its anthropocentrism. In fact, this is not a recipe for the emergence of complex life in general, but a recipe for the emergence of man. We are looking for life similar to ours, and we are surprised that the conditions for it are so rare. But who said that life cannot exist in completely different forms? Life under the ice, Jupiter and Saturn's moons, such as Europa and Enceladus, hide global oceans of liquid water under their icy crust. Energy for life that can be provided by tidal forces and hydrothermal vents on the bottom, like black smokers on Earth. These worlds are far outside the traditional habitable zone. Different biochemistry, Saturn's moon Titan has rivers and lakes of liquid methane and ethane. Is it possible for life to exist on methane rather than water? We don't know. Earth is not so unique. Some of the arguments for the hypothesis are weakening over time. For example, recent data suggest that Earth-sized planets in the habitable zones of Sun-like stars may be quite common. Conclusion: the silence of the stars and our place in the cosmos. The unique Earth hypothesis offers a sobering, if somewhat frightening, perspective. It makes us appreciate the fragility and uniqueness of our world. Perhaps we really are alone, and the silence of space is not a mystery but the default state of the universe. This places an enormous responsibility on us to preserve the only island of intelligence we know of. However, science does not stand still. The James Webb Space Telescope is already analyzing the atmospheres of exoplanets in search of biosignatures, chemical traces of life. What if we find them? The discovery of even the simplest microbes on Mars or in the ocean of Europa will be the greatest discovery in history. But paradoxically, this may also be the most alarming news. If life arises easily, then why do we not see traces of intelligence? This means that the great filter, some insurmountable obstacle to development, is not in the past, the emergence of life, but in our future. And this conclusion is much more frightening than the thought of complete loneliness. Another unique feature of Earth is its air, the atmosphere surrounding the planet. Earth's air is a cosmic rarity. No other planet in the entire universe has an atmosphere like Earth's. On a universal scale, Earth's atmosphere is not just a mixture of gases, but a unique combination that sustains life. That is why it is so exceptional. A composition suitable for life. Nitrogen, sulfur, and oxygen, the perfect balance for breathing for most living organisms. The presence of carbon dioxide, water vapor, and ozone, crucial for climate regulation and protection against ultraviolet radiation. On other planets, even within our solar system, atmospheres are either too thin, Mars, or consist of toxic gases, Venus, carbon dioxide, and sulfuric acid. According to the unique Earth hypothesis, planets with such characteristics are extremely rare. For an atmosphere suitable for life to appear, the following are needed: a stable orbit and a moderate distance from the star, a magnetic field that protects from cosmic radiation, geological activity that sustains the carbon cycle. Life that performs photosynthesis is impossible without air, which means no oxygen. The atmosphere regulates temperature, protects from meteorites and cosmic radiation. Most known exoplanets are either too hot, too cold, or have hostile atmospheres. Even if there is air somewhere, its composition, pressure, and temperature are most likely incompatible with life as we know it. Another uniqueness of Earth's atmosphere is sound. All living organisms on Earth can produce sounds thanks to the air, and humans can combine sounds into words. Thanks to the air, we can talk, we can listen to music, we can enjoy the singing of birds. We can shudder at thunderstorms and lightning strikes. We can fall asleep to the sound of rain. We can daydream to the sound of waves crashing. We can speak words of love to each other. We can lull children to sleep. But all of this is, for the most part, a side effect. What is heard in the universe at this moment, nothing, dead silence. A meteorite has fallen. Heaps of fragments, clouds of dust, silence. Stars explode, collapse, and again silence. Galaxies merge, stars collide, and again silence. So, yes, we are literally breathing cosmic privilege. And it leads to the thought that the air was created artificially and is held on Earth intentionally. So, what was the Earth created for? Specifically created deliberately for the fulfillment of a very specific task, and this task is the accumulation and transmission of energy. All these unique conditions were prepared for this purpose. All these conditions contribute to the existence of living organisms, their functioning, which allows them to perform one and only one task. For comparison, one can give the example of a poultry farm. Greenhouse conditions. A certain temperature is maintained. The chickens are fed, cleaned after, and monitored for their condition. Our Earth is an energy farm, and as for what means are used for this and how it is done, I will tell in my next releases.